What's going on, everybody? We are now in the second half of introducing you to a set of tools that greatly extend the capabilities of these trigonometric functions, namely extending them into the area of working with triangles that are not right triangles. The first one we took to look at was the law of sines, and that's a very, very powerful tool, but there are some instances, like for example, when you're dealing with triangles and you know all three side lengths, but you don't know any of the angles, in which the law of sines really doesn't help you very much. In this case, we have to turn to its sister law, the law of cosines, and that's what we're going to be discussing today. But first, let's take some time here to focus on our breathing and to get ourselves to a point where we can empty our mind of thoughts and we can get ourselves to a place where our minds are clear. This becomes all the more important during times in which perhaps we're sitting at home all the time, watching movies, watching television, surrounding yourself with content, inundating you with a lot of different information. It's hard to turn that off and to find yourself in a place where not only is everything off out there, but everything is off up here as well. It's a time in which you can take a deep breath and enjoy some silence and some stillness within you. Take some time to embrace that. Welcome back. Well, we started last time with deriving the law of sines. That's exactly how we're going to start this session here as well. We are going to derive the law of cosines here. And let's start with an arbitrary triangle, ABC, on corners with lowercase side labels here as well, A, B, and C. And in this case, we are taking a vertical segment from B to an unlabeled point here. It intersects B and it intersects side B here at a right angle, dividing it into two segments, D and E. Okay, and so let's see what information we can derive from the two right triangles that we have within this arbitrary triangle. So in particular, what are some relationships that involve h, this length here h? And the first one is that the sine of A should be equal to h over c. That makes sense, opposite over hypotenuse. And we can solve that for h by saying that h is equal to c times sine of A. All right, that's one. We can also do the cosine of A, which should specifically be D, not B. That extends all the way out here to C. We just want to go this far. So that's going to be adjacent over hypotenuse. In other words, D over C, which, again, we can solve for D by saying that D is equal to C cosine A. We can also solve for E by saying that E is simply B minus D. Since D and E make up B here, then D minus B should equal E. And since we have something here for a value here for D, then we can substitute in for D this expression here, C cosine of A. And then we have Pythagorean's theorem here. The side A is a hypotenuse of this small triangle here. So this squared should be equal to this squared plus this squared. A squared should be equal to h squared plus e squared. Makes sense? Okay, so if we plug in some of these values here, a squared should be equal to h squared, and h is this right in here. So c sine of A now becomes c squared sine squared of A. And b minus c cosine A can be plugged in for e squared. So instead of b minus c cosine A, we now have b minus cosine of A quantity squared. And we want to expand out this binomial being squared here by foiling it out. The first term is going to be b times b, or b squared. The last term is going to be c cosine A times c cosine A, or c squared cosine squared A. And then the two middle terms will be the same. This will be b times c cosine A, actually negative bc cosine A, and the second term will be the exact same. So we'll have 2bc cosine A, both negative. Okay, now notice here I've got a c sine squared of A, and I've got a c squared cosine of A here. If I factor out a c squared out of those two terms, then what's going to be left over? You might find something very familiar in there, and as it turns out, we do. If we factor out this c squared here from those two terms, we get sine squared A plus cosine squared A, which of course we know is just 1. So this just becomes a squared minus b is equal to b squared plus c squared. And then we have this additional term here, minus 2bc cosine A. All right, it's right there. And as it turns out, this is just the expression here for A. There are similar expressions here for B and C, and they actually have very similar forms to this. We don't have the distinction any longer of the hypotenuse versus the legs. All three sides are treated equally and have almost precisely the same forms of this equation here. Let me show you here. Here's the form that we saw just a moment ago, and here are two other forms. You can see they have pretty much the same formula here. If you recall, when you had to use the Pythagorean theorem, c squared was always by itself. C squared equals a squared plus b squared. That's and so if you wanted to solve for b squared, then it was c squared minus something here. So if you had addition on this side, c squared had to be on the other side here. Notice that's not the case here with these laws of cosine here. A squared is equal to b squared plus c squared. And notice the pattern here. We have a squared here, so we have b squared plus c squared minus 2bc. It's b and c that you're going to see repeated here. Everything but a, essentially. Minus 2bc cosine. Okay, we're back to a here now. Just notice that pattern with these other ones here. B squared, the other two sides are a and c, so a squared plus c squared minus 2ac, cosine back to b, cosine b. c squared. The other two sides are a and b, so this is a squared plus b squared minus 2ab cosine c. We can use this to solve a triangle, just like I said before. We can use this to solve a triangle for which we know all three sides, but none of the angles. We can't do this using the law of sines. We really need the law of cosines here. And the way to do this is to focus on the largest angle here. In this case, you can always tell what the largest angle of a triangle is going to be, even if you don't know any of the angles. If you know all three sides, then you know which angle is going to be largest. And you can kind of see it here from this picture here. The largest angle will always, always, always be opposite the longest side. Okay, and so which angle do you think is the smallest angle? Well, that's going to be the angle that is opposite the shortest side. That's true for every triangle. The opposite side is opposite of the longest opposite side. The longest side is opposite the largest angle, and vice versa. And the shortest side is opposite the smallest angle. So let's focus on the largest angle here, A. And so by focusing on that, I mean let's use the law of cosines here to find this angle here, cosine A. So this is a little challenging here. We want to solve this law of cosines expression here specifically for cosine A, which means getting all the other terms on another side here and then dividing by 2bc. So there's a little bit of algebra that I've glossed over here, but hopefully you can see how this works here. If I take minus 2bc cosine of A and move it over here, and then take a squared and move it over here, you can see that's going to be a minus a squared over here. Minus 2bc cosine A becomes positive 2bc cosine A, and I have to divide off the 2bc in order to get cosine A by itself. So this is oftentimes accepted as an alternate form of the law of cosines here, because you can see here this it's one of the most common uses of the law of cosines here is to find out the size of the angle represented in the cosine here. So, okay. B squared plus c squared minus a squared, we know all three of those, over 2bc, again we know everything, so we can plug in these values for each one of these sides, and we get the cosine is negative 0.4509. Now let's take a moment to think about this. The cosine here is negative. Where is cosine negative? If we start off in quadrant 1 here, remember cosine is all about the x direction. All right, so starting off here, once we get up to 90 degrees, up until now cosine has been positive, and it's only now that we're in, it's only when we get into quadrant 2 that cosine starts to turn negative. So what does this tell us here? That this cosine of this angle here is negative. It tells us that we're in quadrant 2. It tells us that A is going to be an obtuse angle larger than 90 degrees. And in fact, that's what we see when we plug this into our calculator and we get 116.8 degrees. Now that tells you something important about this triangle here. There are two different kinds of triangles other than right triangles. There's acute triangles, in which all three angles are less than 90 degrees, and there's obtuse triangles, for which one angle is greater than 90 degrees and the other two are smaller, obviously. And this tells you that this is an obtuse triangle. So B and C should both be actually significantly less than 90 degrees in order for this to work. We can then use the law of sines in order to find the size of angle B here. Sine of B over 14 should be equal to sine of our new angle here, A of 116.8 over 19. We can solve this for sine of B, and we get 0.6577, which means that B is equal to 41.1 degrees. How do we find angle C? Well, that's the easy part. We can just take these two angles here and subtract them from 180, and we get this small angle, 22.1 degrees. All right, so take some time to work on this one here. This is a similar triangle here that has three angles, all three of which are unknown, but whose sides are all known. A is equal to 6, B is equal to 8, and C is equal to 12. Take some time on that one. Welcome back. Well, this involved using the law of cosines to solve for the largest angle. We could tell that C was the largest angle by noticing that side C is the largest side here. And so we used the law of cosines to find out what the value of angle C is, 117.28. Once again, we discovered that this is an obtuse triangle. We then used the law of sines to solve for one of the other angles. Perhaps you used the law of sines here to solve for angle B. That's fine. And in so doing, you should have gotten the same answer here for B that we got here at the end. Here's how we used the law of sines here to solve for angle A, and then we subtracted C and A from 180 degrees to get angle B here. Okay, well, let's take a look here at side angle side here. This is another example here in which we are taking a look at what information you're given here. And as you recall, this was one of our questions from beforehand, is knowing one side, the angle in two sides rather, that are next to each other like a pair of scissors, and the angle in between those two pair of scissors. Is that enough information to determine a triangle? We found that that was enough, in fact, because you could just connect those remaining 2 points with another side, and that became side B here with the dotted line. So we're given a triangle here that has one side that is 9 meters, another one that is 25 degrees, and a third one that is a third side here that is 12 meters. So two sides, one angle here. Here's the issue that we run into with the law of sines. The law of sines always involves the sine of an angle divided by its opposite side. And that's equal to the sine of another angle divided by its opposite side. That's equal to the sine of another angle divided by its opposite side. So we're always dealing with opposite angles and sides. And so we really need to get a pair of opposite angle side in order to solve for everything else. We need to get a pair of opposites, both of which we know, in order to really use the law of sines. We didn't have that when we knew all three sides, but none of the angles, because we didn't have an angle side pair that we knew. That's also the problem here. Notice, I know this side, but not this angle. I know this side, but not this angle. And I know this angle, but not this side. So I can't really use the law of sines here. That's the issue that we're running into. We have to rely on the law of cosines in order to do this here. And in this case, we are using the law of cosines in order to find this opposite side B here, because we can solve for this. B squared is equal to A squared plus C squared. We know both of those. Minus 2AC cosine B. We're using the three things that we know in order to solve for side B. And here we just plug things in. And in so doing, we get 5.4 meters as our value for side B. We have to take the square root of both sides when we, after we multiply these things out and add and subtract them. But now that we have a pair of opposites that we know the length of this side as well as the size of this angle. Now we can use the law of sines to do everything else. So sine of A over 12, so in this case it's A that we don't know. That's equal to this ratio that we do know, sine of 25 degrees over 5.4. We can use this to solve for sine of A, and that is 12 times this, which becomes 0.9379. This is going to be a pretty large angle here, so 69.7 degrees. All right, so we've got 69.7 degrees, 25 degrees. What do you suppose this last angle is going to be? Well, it's going to be found by getting rid of me here and then subtracting these two angles here from 180. And that gives us an angle of 85.3 degrees. So in this case, once again, we're able to use the law of cosines to solve for missing angles, and in particular, a missing angles or a missing side, to get us to the point where we have one pair of opposites that we know. So here's an example here. Much like what you just saw before, we have two sides and the angle in between them that they both know. Take some time to do this and make sure that you draw the triangle here so geometrically you can see in your mind what exactly we are doing here. Think about which form of the law of cosines you want to be using here, what do you want to be solving for, and in doing so, get that one pair of opposites that you know so you can use the law of sines to do everything else. Take some time for this. Welcome back. Well, you're probably starting to notice that we usually use the law of sines with the law of cosines. We're usually using both of them in tandem in order to solve a problem on a triangle here. You can see we use the law of cosines here to find the opposite side to angle A. Once we had that, we used the law of sines. Did I say law of sines or law of cosines over here? I think law of cosines to find the value of this opposite side here. Then we use the law of sines to find one of the other angles. We found the third angle by subtracting it from 180. So there's really three different methods here of finding each of the three unknowns to this problem. Okay, let's take a look at a way in which we can make use of this. Here's an example here from sports. The pitcher's mound on a women's softball field is 43 feet from home plate. So the distance here from the pitcher's mound to home plate is 43 feet. And the distance between the bases is 60 feet. So we've got, at the very least, a rhombus here, most likely a square. Oh, we've got two right angles. It's a square. And the pitcher's mound is not halfway between home plate and second base. So the pitcher's mound here is not in the center of the square. That's an important piece of information here. How far is the pitcher's mound from first base? So we're really asking the what the size of this side here, H, is. Well, we've got, let's see, we know the length of this side. We know the length of this side. We know the size of this angle here. It looks like we've got a side angle side type scenario here, and we can use the law of cosines to find the value of side H here. H squared is equal to 43 squared plus 60 squared minus 2 FP. So this is F squared plus P squared minus 2FP cosine of H. So that is our form of the law of cosines here. We simply simplify that to 73.4 feet. That's as simple as that. That's how quickly that this problem goes. So here, go ahead and take a look at this problem here. It's very, very much like it. In which case we have the same softball game here. A batter hits a ball to dead center field, and it's a distance of 240 feet from home plate. So the length of this side right here is 240 feet. The center fielder then throws the ball to third base and gets a runner out. The distance between the bases is 60 feet, once again here. How far is the center fielder from third base? So we want to know what this distance here is. So we actually have a triangle here, which has been redrawn here. We know that this distance here is 60 feet. That's the distance between two bases. We know that this angle here is 45 degrees because it was 45 degrees on this side here from the pitcher's mound to first base, so we can assume the same here between the pitcher's mound and third base. We're told that this distance here is 240 feet. We want to know the length of this side A. Once again, this is side angle side, so take some time to figure this one out. Welcome back. Well, it seems reasonable that when you have a line drive shot to center field that's 240 feet, that this distance here that the center fielder throws to third base will be something fairly close to 240 feet. So 202 feet seems pretty reasonable here. And you can see how you solve this, hopefully by using the law of cosines, very similar to the previous problem. All right, here's another example. A ship travels 60 miles due east, so here from A to B, and then adjusts its course as shown below. After traveling 80 miles in this new direction here, the ship is now 139 miles from its point of its departure. Let's say point, not pint. Describe the bearing from point B to point C. So from point B here to point C, we're wanting to know that really the size of this angle, which is not even part of the triangle here. So we'll have to solve for the size of this angle here and then subtract that from 180 to find out the size of this angle here. Or actually, since we're finding the bearing, we'll probably want to subtract this because we want to get the bearing here based on its angle from true north. So we'll have to do some kind of a similar subtraction here, but it'll be slightly different. Let's first of all find the size of this angle B here. It's going to be larger than 90 degrees here, so we should get something negative when we solve for cosine B. As you can see here, we've just solved this for cosine B. I'm actually showing the steps here a little more explicitly than I did earlier. So you can see here b squared comes over here and becomes minus b squared. Negative 2ac cosine b comes over here, becomes positive 2ac cosine b. And if I divide both sides by 2ac, I get this here and this here. Now I'm ready to plug everything in to find out what cosine of b is. And I get, oh, sure enough, this is it's actually very negative. It's close to -1, isn't it? So this is actually, it shows just how close this thing is to a full 180 degrees here. So, okay, so 0.9709. So this angle here is 166 degrees. So how do we interpret that in terms of making this into a bearing here? So what we have to do here is notice, and I'm going to use my pen here, if this angle here is 166 degrees, then we're going both north and east. And so the bearing here should be taken from true north, like this. This portion of the angle here is 90 degrees. So in order to find the size of this angle here, we have to subtract 90 degrees from 166, and we get 76 degrees here. So it is north 76 degrees east. Okay, here's a similar problem here. A ship travels 40 miles due east and then changes direction. Here we go from A to B, 40 miles due east, changes direction as shown in the figure. After traveling 30 miles in this new direction, the ship is now 56 miles from its point of departure. So describe the bearing from point B to point C. So you're going to have to find what this angle is and then figure out how to translate that effectively into a bearing. Take some time for that. Welcome back. Well, once again, you use the law of cosines to focus on finding the size of a particular angle here, in this case, angle B, in which case we found out that it was an obtuse angle since cosine here was found to be negative. The size of the angle here was 105.4 degrees here, and similar to what was done in the previous slide here, we had to turn this total angle size here of 105.4 degrees into some bearing for this direction here of the vehicle. Okay, so we knew that it was going north and east, so it's going to be north some degree value here east, and the way that we find that is to take 105.4 and subtract off the 90 degrees here going from due west to due north, leaving behind 15.4 degrees east, which is what our answer is. Okay, so we've oftentimes been studying in this particular chapter here, a lot of new ways in which we can find the area of a triangle. And so it's pretty fitting here that we get a third means of calculating the area of a triangle. It's this really ingenious formula here from a Greek mathematician, Heron of Alexandria, about 100 years BCE. And basically what it is, it's a formula for finding the area of a triangle, again, just using the lengths of the three sides. You don't have to know the size of any heights or any altitudes. No lines have to be drawn from an opposite corner to another side, ending at the side. And here you actually don't even have to know any trigonometry in order to solve this here. So were it not for the fact that this formula is somewhat complex here, this would probably be a formula for the area of the triangle that would be introduced earlier in school curriculums. But essentially what it is you first have to find this variable s here, which is a plus b plus c, all three of those added together divided by 2. And believe it or not, the size of the area of this triangle is just the square root of 4 things multiplied by each other. S times s minus a times s minus b times s minus c. If you multiply those 4 things together, then take the square root, we get the area of a triangle. And we can use this along with some of the others. So we now have 3 ways in which we can calculate the area of a triangle. The first one is the one that you learned earlier, the 1/2 base times height formula here. You have to know the size of this height here, the distance from one side to an opposite angle here. So you can actually think of it as height. If this triangle is resting on side B here, then it's literally the height of the triangle here. How high does this upper peak here go at B? It goes to a height of h. The second means is to use these 3 formulas which we came up with, 1/2 BC sine of A, or 1/2 AC sine of B, or 1/2 AB sine of C. And the third is Herons formula. This is the one that we just found here, which involves multiplying 4 things together and taking the square root. And part of what you have to find before doing all 4 of those multiplications is this value here, s, which is a plus b plus c, all divided by 2. All right, so let's use Heron's area formula here in order to find the area of a triangle. The area of a triangle, this particular triangle has sides of 43 meters, 53 meters, and 72 meters. So that's A, B, and C. So we can very easily here find out what S is by just adding those together, dividing by 2. We get 84. And so our area formula here now becomes 84 times 84 minus 43, 84 minus 53, 84 minus 72. So we've got to do these subtractions here first before we do any of the multiplications. So this becomes 84 times 41 times 31 times 12. All 4 of those multiplied together, and that gives us a large number, which then when we take the square root of it, we get 1131.89 square meters. M squared is the way in which we describe square meters in terms of units. All right, so use this formula here to solve the area for this triangle here. It has side lengths of a equals 5, b equals 9, c equals 8. Take some time for that. Welcome back. Well, we always like problems that have really straightforward formulas that you just have to plug things in order to find the solution here. That was the case here with using Heron's area formula in order to solve for the area of this triangle here. We found that S was equal to 11 and that the area was equal to the square root of 11 times 6 times 2 times 3. The square root of that was 19.9. Okay, so in summary, as we take a look at all the things that we discussed today, we've gotten the second half of these wonderful things that you can use to apply trigonometry to some non-right triangles here. First one was the law of sines. The second one, the law of cosines here. So do you know how to use the law of cosines to find unknown sides and angles for triangles? That was really the big thing that we discussed here today. Something that was kind of an addendum that was added on near the end was also Herons Formula to find the area of the triangle. That's now the third item in the pantheon of formulas that you now have for solving for the area of a triangle. And lastly, we used this to solve some real problems here. So did you make those connections between the abstract and the real to be able to use these tools in order to solve some real problems in the real world? So hopefully this has been very, very helpful for you. Be aware that there's an assignment that's due that will cover a lot of these things here, and I'll see you in class.